Hi everyone, welcome back to Unit 3 Chemistry for QCE. Today we're going to be continuing with topic 1 and we're going to do equilibrium constants. So if you recall in the last video when I mentioned something called QCE and I was like, I'm not going to tell you what this is. Well, now I am going to tell you what it is. So let's get started. But before we get started, please like and subscribe so that you can get a good ATAR and I can be happy. Thank you. Okay. So equilibrium law expression, that's the first thing that we need to know. So what is that? Equal law expression. Basically, it's like this little equation. Ew, maths, I know. Kc equals concentration of products over concentration of reactants. And that's the easy version of this formula. There is a more complicated version, but that's kind of what you need to remember in your brain. And then this other one is like on the formula sheet, but it just kind of makes it easier to conceptualize what's going on if you think of it this way. The official one is a little something more like this. Again, remember that these square brackets mean concentration, as I have mentioned before. And what this expression is basically telling us is how to calculate this thing, Kc. So basically what's going on here is that this is a specific version of this equation, but for the reaction, AA plus BB goes to CC plus DD. Okay. And so this is like some reaction where these are the reactants and these are the products. What we can see is that we have our products on top, where we have the concentration of this molecule to the power of whatever like number of moles it has. And then same for everything else. So then we have the products on top and the reactants on the bottom. And so Kc is actually basically just a special number, and we call it the equilibrium constant. And what it tells us is the ratio of the concentration of products to the concentration of reactants in any particular equilibrium system. Some important things to remember about this is that, it only includes aqueous and gaseous molecules. And that is because solids and liquids don't really have concentration, they kind of just exist, right? Like if you have a cup of water, it's just a cup of water, right? Or like if I have like a little piece of gold, it's just a piece of gold. It's not like, oh, like it's super concentrated. The only reason that you would have concentrations of things like that is if there's like other materials mixed into it. But for the sake of like grade 12 chemistry, you can just ignore anything that's a solid or liquid. You would only worry about aqueous or gaseous things because they kind of have concentration, whereas solid and liquids, pure solids and pure liquids don't have concentration. Another thing to keep in mind is that these expressions can be written for 1, homogeneous systems, and 2, heterogeneous systems. So you might be wondering, what is that? Homogeneous system is where everything is the same, and this one is where things might be different. And what I mean by that is, in a homogeneous system, it would be like if you're having like a glass of milk, right? Milk is technically an aqueous solution with a lot of different molecules in it, but they're all spread out super evenly, and so like when you drink one sip of milk, that wouldn't be different from like a later sip of milk that you have because all of the molecules are like evenly spread out. Technically milk isn't a solution, but just allow it. The opposite would be a heterogeneous solution, where like say if you have like a cup of cordial, but like whoever made the cordial is really dumb and they didn't mix it together properly, so you have like at the top just water and then at the bottom you just have cordial. So like one sip at the beginning would taste like totally different to a sip at the end where it's like you're just drinking like straight sugar. So what that would be is a heterogeneous system because there's differences in the chemical composition at different points in the mixture. So like in milk, no matter what like little point of milk I look at, it's all just got the same chemical composition, but in this like weird cordial, if I look at the top, there's like a different concentration of different things as opposed to the bottom where there's a different amount of concentration. So the official definition is that in a homogeneous system, properties are the same throughout the entire system, and in a heterogeneous system, properties differ at different points in the system. However, you only need to be able to deduce the equilibrium law expression from equations for homogeneous reactions. So you need to know about these two different things, but they're never going to give you a question where it's like, oh, figure it out for a heterogeneous one. You can just assume it's always a homogeneous system, so don't really need to worry about this. Still know what it is though, because just in case they ask, because QCE does stuff like that all the time, where they ask totally random questions. Okay, so Kc is our equilibrium constant. It's very important. Again, this is something that you will become intimately familiar with, or maybe you already are. And it, as I said, indicates the relationship between product and reactant, so it kind of gives us like a ratio of product to reactant concentration. Should probably add my brackets. But there's something very important, which is that it's specific to a certain temperature. So Kc changes depending what the temperature is, and that is because, as we discussed earlier with Le Chatelier's principle, changing the temperature causes changes in the equilibrium position, and so it doesn't really make sense if we assume that the ratio of products to reactants is going to be the same at every temperature. This goes back to the example that I kind of talked about in the first video. So say you have these different situations where you have like different ratios of water to ice, and keep in mind that the ice is constantly turning into water and the water is constantly turning into ice because it's the equilibrium system. These different situations will occur probably at different temperatures, right? Like this one would be colder, this one would be hotter, and this one would be probably like pretty neutral. So it's kind of unfair of us to say that the ratio of products to reactants is the same in all of these, because it's clearly not, right? And so this is just a really obvious example of why Kc can only exist at a specific temperature, but this same concept still applies to like every other equilibrium situation, even when you can't clearly see like, oh, this is ice, this is water. It will still change depending what the temperature is, and so that's why Kc is only accurate for the specific temperature that it's calculated at. Next thing is, it doesn't have any units. Okay, then what is actually the point of calculating Kc? Like, why do we need this? It's because we can use it to predict the relative amounts of reactants and products, and therefore we can figure out what is the equilibrium position, or what is getting favored, or like, are there more products than reactants? And the way that we do this, if we have a big Kc value, which is kind of defined as being greater than 1, then what that means is there's more product. So that would mean that the position is to the right, because we're favoring the products, right? So it's reactant to product. So that's why it would be to the right. On the other hand, if Kc is less than 1, then that would mean that we have more reactant. And that would mean that our equilibrium position is to the left. We have a third option as well, which is when our Kc is exactly equal to 1. And in that situation, we would have an equal amount, so there's like no favoring. The reason why this works, and the reason why we specifically use the number 1, is because if we, again, go back up to this equation, this is why it's important to, like, think of this products reactants equation, because it helps you conceptualize what is actually going on. Like, if you just think of this as a normal fraction, right, where you have, like, the number 1, and then you have the number 2, this clearly is showing you have less products than reactants, you have twice as many reactants, and literally the Kc value for that would be 1/2. Just normal fractions. Very normal, very simple, easy fractions. However, if I have 2/1, then that clearly shows us I have more products and less reactants, and in that case the Kc value would be equal to 2. And so if for some reason I have like 3 product and 3 reactant, my concentration of products is 3m and my concentration of reactants is 3m as well, then that would cancel out and give us a Kc value of 1. And so we can see that literally just because of the way that fractions and like division works, if we have more products, there's more on the top side, then we're always going to have a fraction that's greater than 1. And if we have more on the bottom side, then we're always going to have a fraction that's less than 1. So that's why we use 1 as like this deciding factor. So when we have this case, we say that the equilibrium position is in the middle, because neither side is being favored. Alright, the other thing that you can do is you can use the magnitude of the equilibrium constant to deduce the extent of the reaction. And that's kind of a weird word, like what does extent mean? There's two kind of things that it means. The syllabus doesn't really specify what it wants you to do with this, so it's a bit weird, but generally the two things that this refers to is something called yield, and then there's like another thing called reaction quotient. So let's talk about yield first. So what's yield? Yield is like, I don't know if you've ever played like Farmville, but yield is like the amount of crops or like the amount of stuff that you get. So similarly in chemistry, when you get a lot of product being produced, like if I am cooking a cake, right, I have my like reactant ingredients and then my product is cake, like I'm trying to get cake. And say if I get a lot of cake, a lot of product, then that would mean that I have a high yield because I got a lot of what I wanted to get. And so therefore, having a larger Kc value, big Kc means more product, and more product means more yield. So that's literally it. So then we would say we have a higher yield when we have a bigger Kc. So that's how you use Kc to predict what is the yield of a reaction. The higher your Kc is, the more the products are being favored, the more concentration of products you get, and the higher the yield would be. And if you have a less than 1 Kc, then that would mean that your reactants are being favored, so then that would mean you have bad yield or low yield. The other thing is reaction quotient, which is QC, which is like Kc, but it's a fake. because Kc is specifically the equilibrium constant, right? But what if a system isn't at equilibrium, then what are we supposed to do? So basically they made up like a Kc dupe, and they called it QC, and you can just predict a couple of things by using QC. So what you can predict is how close the system is to reaching Kc, because the closer your QC is to your Kc, the closer the system is to equilibrium. And then the second thing is, it lets you predict which direction it needs to go in order to get to Kc. So if your QC is close to Kc, let me start writing this down for you, then that means that it's almost at equilibrium, so closer to equilibrium. If your QC is less than Kc, also, like, by the way, if it's like equal, then, you know, that would mean that it is at equilibrium. Okay, and then if your QC is less than Kc, we need to favor the forward reaction in order to get to equal being equilibrium. And then if your QC is more than Kc, then you need to favor the reverse to get to equilibrium, because it like needs to go backwards. Okay. Hopefully that makes sense. Now, using Kc, I don't know if you've noticed yet, but it's quite mathematical. So usually when you're asked questions about Kc, it's something related to maths and something related to calculations, which might annoy some of you, because I know that it definitely annoyed me, because I was like, this is chemistry, why am I doing maths and chemistry? Whatever. Corb. I'll teach you an easy way to do it though. So the main things that they ask you to do is they either ask you to calculate Kc, or they give you Kc and then they ask you to calculate the concentrations of things. So calculating Kc is pretty okay, because they do literally just give you this formula in the data book. So all you have to do is get a balanced equation, and then you can just substitute everything into here, and I'll show you an example of that in a second. Or the other one is a bit trickier, which is where they give you Kc and then they ask you to figure out the concentrations of the things involved. Okay, let's not freak out. Let's think about some steps, okay? First thing is, you would usually be given basically all the information required to write a complete equilibrium law expression, but just be asked to fill in 1 or 2 blanks. And those blanks could be like Kc itself, or just like 1 or 2 of the concentrations. But you'll never be given just like, oh, like 1 concentration, then you have to figure out like 5 other things. It would always be just like 1 or 2 things that you need to figure out, so it's not that bad. Secondly, you will never have to do quadratics. If you do methods and you know what quadratics are, you will never have to do those in Chem. Even if they give you a question that looks like you need to use quadratics, you don't. And what you do instead is that if Kc is really small, then you can assume that your initial reactants, I'm just going to write R initial, is equal to your final concentration of reactants. Final as in like at equilibrium. But just make sure to state that assumption in your response. So if you're writing this down in an exam, just say that this is what you're assuming, and then once you do that, you should be able to solve the rest of it without needing to use any quadratics. Okay, so yeah, if you ever get to the point where you're looking at something and you're like, this is a quadratic, you don't need to solve it. You can just make up this assumption and then you're good. So, how do we actually solve these problems where, you know, they're asking you to figure stuff out that you don't know? I have some steps for you, and I would really recommend you listen to these steps, because they're going to save you when you get one of these fat 6-mark questions in the external exam. So, listen. So number 1 is get the balanced reaction. You need a balanced chemical reaction if you're going to do anything else, okay? You need to do this. They will give you a mark for writing this down as well. So even if you literally don't know what to do at all, if you literally just write down the balanced chemical equation, you will still get at least 1 mark for that. And just make sure that you are using your equilibrium arrow and your state symbols. Otherwise, you will not get your mark. So don't do stupid stuff like that. Then the next thing you're going to do is draw and fill in the Rice table. So the Rice table basically stands for ratio, and then initial, change, and then equilibrium. What we do is we literally write this out as a table, okay? And these two are referring to concentrations, by the way. So this is talking about the concentration at the start and the concentration at equilibrium. Say that our balanced equation here is like 1a plus 2b goes to 3c plus 4d. And let's just say these are all aqueous. Sorry, don't forget your state symbols. So then what we're talking about here is a, b, c, and d. And our ratio is 1, 2, 3, and 4. And when I say ratio, I literally just mean the molar ratio, so that would be like whatever number is before the molecule. And that tells you like how many particles of it are getting produced or used up every time. Then we write down our initial concentrations. So let's say in the question that we've gotten, they tell us the initial concentrations of the reactants, and they tell us that there's no product, so that means 0 concentration, because they don't exist. Then what we need to do is figure out the change. So the change is literally going to be just your molar ratio, but times by x, because we don't actually know what the change is between the initial concentration and the equilibrium concentration. what we have to do is just like make up a number, which will be x, but what we do know is the ratio of how much is changing. And that might not make sense, but what I mean is every time we have this forward reaction happening, we use one of the A molecules and 2 of the B molecules, and we get 3 of the C molecules and 4 of the D molecules. And what we can do with that information is that we basically know that every time the reaction occurs, the number of B molecules we use up is twice as many as the number of A molecules we use up. Also, the number of C molecules that we get is 3 times as many as the number of A molecules that we used up. Or, the number of D molecules that we get is twice as many as the number of B molecules that we use up. And so, what we can do is basically by using these ratios, we can assess, and we know that every time I lose 1x of A, right, at the same time, I lose 2x of B, right? So whatever change I have in A, however much my A value or my A concentration is getting reduced by, I know that my B concentration is getting reduced by twice as much. And I know that my C concentration is getting added by 3 times as much, right? Because it's a product, so like it's increasing. And then for D, we know that our D concentration is increasing by 4 times as much. So basically all we're doing is we're just like converting this ratio into something with an X. And we put a negative on the reactants and a plus on the products. Then, say we're told that at equilibrium, our concentration is C for this and D for this, just like for fun. So what this looks like now is that we need to figure out what is our A concentration at equilibrium and what is our B concentration at equilibrium. And the reason that we use this rice table is just because it lays out all of the information really easily for us. We can really quickly see what is the information that we have, what is the information that we need. And that is something really important when you're doing any like maths question in Chem or like in any science. You always need to have it really clear what is all of the information that they've given you and what is all the information that you need to work out. And that's like one of the things that guarantees that you get full marks. For equilibrium concentration, what we need to do is we need to figure out these 2 things. How are we going to figure them out? Well, fortunately, we know that the initial concentration for A is like A. And then we know that the change is minus X. And similarly for B, we know it's going to be B minus 2X. Right? So it's this initial value and this change is what gives us the equilibrium. And similarly to this, we've got the initial value and the change. That's what gives us this. We also know that this C is equal to 3x because 0 plus 3x gives us C, right? So that means we have to know that like 0 plus 3x equals C, therefore C equals 3x. Same thing with D as well. We know that 0 plus 4x has to equal D as well. So since we know that C is equal to 3x, right? We know that C is like some number that they've given us. So this one, and this one, and this one. These are all numbers that they've like provided us with. And so say like C is just equal to 9 or something, and then that's 3x. We know that x has to be equal to 3, and that would probably be like 3 moles because we're working with concentrations here. What that would mean is that, let's say B is like 8, right? Then we just do some simple algebra here. So this is equal to 8 minus 2 times 3, and that would give us 2. That would be our concentration at equilibrium. And then for this one, let's say 8 was like, I don't know, like 5. The initial concentration was 5. And then so here again, we do some simple algebra. We have 5 minus 3, and then that gives us 2. That's basically how this works. Sometimes it won't be this situation where they give you like 0 concentrations at the start. Sometimes they won't even tell you that it's 0. They would just say that like, oh, we've just added the products in. So you would have to assume that the product concentration has to be 0. So sometimes they'll give you like secret information like that, where they don't explicitly tell you that, oh, the concentration is 0, but they'll just tell you like, oh, there's none of it. Then you would know that obviously concentration has to be 0 if it's not there. And then the other thing is, no matter what the situation is, it'll always have to be the case that you have one pair that matches up so that you can make some kind of equation like this. Maybe these might not be the unknowns. Maybe like 3 of them are unknowns, but at least one of them would have to have like a matching pair where you have a number for the initial and you also have a number for equilibrium. And then you can figure out what X is, and then you can use that to figure out what everything else is. So at least one of the products or reactants will have to have like a matching pair for you to be able to work out the X. So once you do this, now what? Finally, the last thing that you would usually do, so step 3, would be to calculate KC. So usually these questions are ultimately asking you to calculate KC, like that's why you're trying to figure out all the equilibrium concentrations. And if that is the case, don't forget step 3, because you'll just like waste like 2 or 3 marks in the question if you just forget to calculate KC. So usually that is what they want. Sometimes they just want the concentrations, in which case, yeah, obviously just leave it as the concentrations, but usually they do ask for KC. So then calculate KC, and then for that you obviously just use your usual formula, which is products of reactants. And that is pretty much it. And then make sure to just give like whatever information they've asked for with the correct units, double check your work, etc. Okay, let's do a practice question. Say you have 2 moles of C3H8 and 13 moles of O2, and they're put in a sealed 20-liter container. At equilibrium, there is 150 moles of H2O. Calculate Kc. So, first thing I'm going to do is figure out a balanced equation. So step 1, balanced equation. You don't really need to write down your steps, but anyway. So we know we have C3H8, and don't forget my state symbols, plus O2, that's going to be a gas. We know that it's in a 20-liter container. I'm just going to underline that for now, but it'll become relevant in a second. And then we know that it at some point turns into H2O. Okay, and then it should turn into something else as well because we have some C in here. Most likely it will be turning into CO2 because this is a combustion reaction. Don't be concerned if you think this is a hard question. This is like, I know it's weird that they didn't give you all of the products and reactants. They usually do. This could be like a part B of a question and they've like given you some information earlier. But for this example in particular, we know that this has to be a combustion reaction because it's got a hydrocarbon and oxygen making water and something else, and that something else is usually carbon dioxide. Okay, then we have to balance this equation. Very important, never forget to balance. I can put a 3 here so that the C matches up. Top tip for balancing equations, you should always do it in this order. So you should do C and then H and then O. So I've got that, and then we have 8H over here, so I'm going to times this by 4. And then I've got 1, 2, 3, 4 plus 6, so that's 10, so this has to be 5. So let's just double check. I've got 3C plus 3C, and then I've got 8H and 8 hydrogen here. And then I've got 10 oxygen, and then 4 oxygen, and 3 times 2, which is 6 oxygen. So that all adds up. That's step 1 complete. Step 2, let me draw my RICE table. So I'm going to write RICE, and remember that stands for ratio, initial concentration, C stands for change, and then E stands for equilibrium concentration. I'm just going to write like 1 extra letter. I'm going to put my actual molecules at the top here. And then I can draw in some lines if I want to, just for funsies. So what I'm going to do now is just try to fill in this table. For that, I can use the information that they've given me. So when you do your RICE table calculations, you can do it either as a concentration. I would recommend doing it as a concentration. Or, if you want to, you can do it in moles. But that only works if you have like a consistent volume. So in this case, you know that there's this 20-liter container, right? If you wanted to, you could do it all in moles, and then at the end you could just like divide by 20 to calculate the concentration, because that would be like your N. So you could do it in terms of N, and then divide by V at the end to get your concentration, because remember, C equals N over V. But I don't really like doing that. Even if they give you molar values at the beginning, like in the question, I would still just convert them to concentration first, because overall it just makes your life a bit easier. Also, I have forgotten to like convert back to concentration at the end, and then you lose marks for that. So it's like, don't do that. So yeah, I would recommend just keeping it simple, working on concentration. So yeah, so I see here, I've got 2 moles at the start, so let me fill in this information. I'll do it in a different color for easiness. Initial concentration is 2m, and then 13m of this. I know, so I can also copy down my ratio from the equations. I have 1 here, 5 here, 4 here, and 3 here. So that's 4, and that's 3. And then I don't know what this is, but they've told me that they've just put these things in a sealed 20-liter container. And so I'm going to say this is 0, because there's like none of it exists yet, because the reaction hasn't actually happened to produce it yet. And then change, I can just write down -x and -5x, +4x, and +3x. So remember, I'm just taking these numbers, adding a x, so timesing by x, and then adding a negative for the reactants and a positive for the products. Also, by the way, I should have put an equilibrium arrow here, because this is an equilibrium reaction. Don't mess that up in the exam. Okay, and then what's our equilibrium concentrations? We only get 1 equilibrium concentration here, which is 150 moles of H2O. And now this is an N value, right? So we would need to actually convert this to concentration. So let's apply this formula. We know that concentration of H2O, by the way, you should write down this working if you do this in the exam. Like, make sure to just write it out somewhere. So this equals N over V, which equals 150 divided by 20 liters, which equals 7.5. And that would be N. So don't forget your units as well. So then we can put in the 7.5 here. Okay, sweet. So now, as you can see, I don't know what it is for this, I don't know what it is for this, I don't know what it is for this. But that's fine, because I at least have 1 matching pair. I have this, right? And so what that means is, I can write out my little equation. So I know that 0 plus 4x equals 7.5. And so what that means is, 4x equals 7.5, which means x equals 7.5 divided by 4. 1.875. Okay, sweet. And that's moles as well. So now we can calculate everything else. So this is going to be 3x, right? So this should be 0 plus 3x, which is equal to 3 times 1.875, 5.625. So that's what I'm going to put in here, 5.625 m. And then I can do exactly the same things for these ones. 13 minus 5x and 5 times 1.875. And then this one would be 2 minus x, which is 2 minus 1.875, which gives us 0.125. So that leaves us basically all done. Yippee! But don't forget step 3, which is calculate KC, because the question asked us to calculate KC. So that means we actually need to calculate KC. So KC equals products over reactants. Let me just write that down. And then this is once again where our balanced equation comes in really handy, because if we didn't have that, I would not be able to figure out the equilibrium law expression. Remember, equilibrium law expression is just the name we give to like this KC equation. So if I just shrink this down, I know that I've got concentration of H2O to the power of 4 times the concentration of CO2 to the power of 3, C3H8 times O2. And then what I do is I literally just calculate this. So remember, all of these concentrations are the concentrations at equilibrium, because it's the equilibrium law expression. I can just copy down the concentrations that I figured out, which is, so it's going to be 7.5 to the power of 4 times to the power of 3 divided by 0.125 times 3.625 to the power of 5. And I'm not figuring that out, but you can if you want to, and you can put it in the comments if you're really nice. So that's pretty much everything for this. The only last point that I would make is that if you get like the opposite of this question, where they give you KC and then they ask you to figure out the concentrations, you just do exactly the same thing but in reverse. So you would write out your equilibrium. You still need to start with a balanced equation. You write out your equilibrium law expression, and then you figure out like what's missing, and then you should still have like all of your other things, or they should still give you enough information that you can fill in the rice table. It's just that instead of figuring out your equilibrium concentration, you would probably be figuring out an initial concentration. Maybe not though, but it should still basically work out exactly the same way. Don't get scared if you see that. Just remember, when you fill out your rice table, you should always be able to find one like matching pair, and then you can use that to figure out everything else. So hopefully that all makes sense. Leave any questions in the comments down below, and I will try to get back to them. And if you want a complete subject guide for chemistry, you can find that in the link in the description, or you can get an active ATAR membership, which gives you access to heaps of educational content for all of the subjects, as well as thousands of practice questions and detailed explanation answers. You can also directly book online tutoring or assignment help sessions on that link. Anyways, please like, subscribe, comment, and send it to your friends if you like them and you want them to be smart.